All right, everyone, we're going to finish up Chapter 9 today, looking at Section 9.3, Tests about a difference in proportions. So some of the learning targets for today, you should be able to state the appropriate hypotheses for a significance test about a difference between two proportions, determine whether the conditions are met for performing a test about difference, calculate the standardized test statistic and p-val for a test, and perform a significance test about a difference between two proportions. So this chapter probably seems pretty familiar as chapter 8. We talked a little bit about what tests are, did them for one sample, and now we're looking at a difference between samples. So some of the things should look very similar. There's one kind of wrinkle we're going to throw in today, but it shouldn't be too bad. So to start off, we're looking at a difference between two proportions. So we're trying to see about p hat or p1 minus p2. So that is going to be our null hypothesis. And we usually do P1 minus P2. The reason why we do that is, well, if you added P2 over, then you would get P1 is equal to P2 as your null hypothesis. And then that would mean that your alternative hypothesis would be maybe is either P1 is bigger than P2 or the other way around, or there's just a difference. So almost always are we going to look at P1 minus P2 is equal to 0. You could write it either way here. So let's look at a problem. Researchers designed a study to compare the proportion of children who come to school without eating breakfast in two low-income elementary schools. An SRS, or a simple random sample of 80 students from one school, found that 19 missed breakfast today. At school 2, a simple random sample of 150 students included 28 who missed breakfast. There's more than 1,500 students that attend both schools. Do these data give convincing evidence of a difference in the population proportion at an alpha of 0.05 significance level? So it's going to follow the same kind of process: state, plan, do, conclude. So at first, we're going to state our hypothesis. So right off the bat, we're going to do P1 minus P2 is equal to 0. So then our alternative hypothesis is that it doesn't equal 0. The reason why we say doesn't equal 0, if I go back, it asks, do these data give convincing evidence of a difference in the population proportion? So it just says difference. It doesn't say that school 1 is bigger than school 2 or school 2 is bigger than school 1. It just says a difference. So with a difference, it just means that it's not equal to 0. They're not the same. So that's why we're going to have a does not equal here, which is going to result in a two-sided or a two-tailed test. Right? Along with stating your hypothesis, you want to state what P1 and P2 are. So P1 is the true proportion of all students at school 1 who missed breakfast today, and P2 is the true proportion of all students at school 2 who missed breakfast. So here's where the big new idea is. When we take significance testing, we always assume the null hypothesis is true. So we always assume it's true. In this case, we're assuming that P1 is equal to P2. Because if we had P1 minus P2, again, you can add that P2 over. You get P1 is equal to P2. So we're assuming that is true. And well, kind of the idea here is if we assume that they're true, then there's got to be some kind of link between P1 and P2. So we actually come up with this kind of combined or pooled proportion for P1 and P2. Since we're assuming that they're true, we're assuming that they're equal, there's got to be something kind of related to them. And so we're going to call this a pooled or combined value for P. So how you get it is it's P hat and it's pooled or combined is what it's called. And it's just the total number of successes in both samples divided by the total number of individuals in both samples. Okay. The reason why we do that is that, well, we assume these are true, so they're probably coming from some larger sample. So there's probably something about them that's a little bit similar. So we're going to go ahead and use that idea like a larger sample to try and build what our P pooled is going to equal. Yeah. So we still need to check our conditions. And so it's going to be the same three: random, 10%, large counts. The random, the data comes from two independent random samples of, in this case, they said simple random samples, or an SRS, so you know that it's random. If it was an experiment, they might say two groups in a randomized experiment, because remember, an experiment doesn't necessarily have samples per se, but their randomization comes from which group they go into. The 10% condition is needed when we're sampling without replacement. So N1 is less than 10% of N1, and N2 is less than 10% of N2. And then lastly, our large counts. So this is the big difference. When we do our large counts, it's actually N1 times P pooled, or P combined, and same thing for the other three. And we're going to check that those are all greater than or equal to 10. So back to this example. Are they random? Well, it said an SRS of 80 students from school 1 and an SRS of 150 students from school 2. So we're good there. Is it 10% good? They stated that there's more than 1,500 students at both schools. So yes, 150 is less than 10% of 1,500, and 80 is also going to be less than 10% of 1,500, which is the minimum that they told us. For large counts, we're going to use that P combined value. So we add 19 plus 26 over 80 plus 50 to get a value of P hat C, which is 0.196. We're then going to take that number to find our successes and failures. And you really should state the information this way. I saw some of us on our test just jumped right to 80 times this is equal to 15.68 and said that's bigger than 10. Or you just gave me the number 15.68 greater than 10. And although that might be fine, the whole point of checking your conditions is to state that they're all true. And so if you just give me the number or give me 80 times this, we don't really know where that information is coming from and what you're really doing. For all we know is you're just stating a random number saying, hey, it is bigger than 10. So make sure you do have these four pieces along with it to kind of show you where that formula is coming from. Since all of our parameters are good though, or all of our conditions are checked and we are passed, we are going to go on to the do phase. So remember the standardized test statistic, or that z-score, we get that from our statistic minus our parameter divided by the standard deviation. So we have z is equal to p hat 1 minus p hat 2 minus 0, and then we have that standard deviation formula of combining two random variables here, two independent random variables. But be careful here. You might just go right in and just plug in p hat 1 and p hat 2, kind of like how you would for the confidence interval. But like I said, this is a one big wrinkle here. So I want to make sure we don't make that mistake. So we actually use the pooled proportion here. So again, we already had that PC or p hat c. So we're going to use the combined pool proportion in place of p to get our standard error in the denominator. Okay, so this is the formula you should use for a pooled proportion, where p hat 1 minus p hat 2, all minus, technically whatever the parameter is, our parameter is almost always going to be 0, divided by the standard deviation. Okay. So still same example. Now that we're just going to kind of explore a little bit, it says explain why. Well, we'll look at part A, B, and C. So A is explain why the sample results give some evidence for the alternative hypothesis. So right off the bat, the sample, we got 19 out of 80 and 26 out of 150. When you subtract those two, you get this number 0.0642. And hey, that is not equal to 0, which we assumed at first. So right off the bat, we have some evidence to suggest that, hey, there might be a difference in the proportion. But again, the whole point of hypothesis testing and confidence intervals is to see, well, how strong is that evidence? How strong is that evidence that it is really different? All right, so although we have some right now, the question is how strong, and that's where our hypothesis testing is going to come from. So part B says to calculate the standard test statistic and the p-val. So first you do need to get your PC, your p hat C to be 0.19, and then we take this formula. Now remember, it is still p hat 1 minus p hat 2. Minus 0 all over. Now we take that pooled proportion and divide by the two sample sizes. Okay. So then to actually find the p-value, we have to take, so the big part we got is z-score of 1.17. So we're going to go from 1.17, so right about here, and we are looking at the difference. We're looking at either bigger than 1.7 or less than negative 1.7. So my 1.17 is here, and I'm going to look shade to the right. And also, since I'm doing a two-tailed, since it could be either bigger than or less than 0, I'm going to take negative 1.7 and shade to the left. The reason why I know I'm shading to the outsides and not shading internally is because I'm trying to see if this value is different than 0. So I wouldn't want to include 0 in my probability. It's going to tell me I'm going away from 0. I'm saying how far away is this from 0. So with the table, because remember our table goes from negative infinity up into whatever z-score, I would probably look at the 1.17 and see that that is the probability of that occurring is 0.1210. And then you can just double it. Since the normal curve is symmetric, less than up until negative 1.17 is going to be the same as 1.17 to the right. Okay, so you can actually double it. If you were to use the normal CDF, you could do the same idea. You could do 1.17 to 1,000 and then double it, or you could do two separate calculations and add them together, but you're going to notice they're going to be the same thing. Okay, so there's a couple ways you could do this, but it's really important to realize if I'm doing a two-tailed test that I do shade in both directions, and I remember to double that value. And then it says, what conclusion would you make based on the alpha being 0.05? And this is going to be kind of the same cookie cutter response we're going to use a lot. Because the p-val of 0.2420 is greater than alpha, which is 0.05, we fail to reject H naught. There is not convincing evidence of a difference in the true proportion of students at school 1 and school 2 who skip breakfast today. So basically, we fail to reject H naught, so we don't have convincing evidence that there's a difference. So we don't have convincing evidence in favor of the alternative hypothesis. All right. Now, the calculator does have these calculations for you. So if you go into your calculator and you go to the tests to try and find them, you could find two prop Z tests. And here you could put x1, n1, x2, n2. You can either state that they're equal or they're not equal, that they're less than or they're greater than. So this really is your alternative hypothesis because, again, remember, our null hypothesis will always be that they equal each other. That's why we use that pooled proportion. So this question is asking about the alternate hypothesis. And then you can calculate it and get a value out. You see here is our p pooled value. It's the same as when we did by hand. And I'm going to say the same kind of warning. I do not want you to do this right away. If you do this right away, you're not going to check your conditions. You're not going to show your work. You're going to make some type of error there, and you're going to lose points, either by making error or just not including the work that you need to. If you want to go ahead and use this, I would highly suggest doing it after you've already done your test, gotten your p-value, and once you got your p-value, then you can run this as a kind of way to check your work. And then you can see, okay, I got the same p-value, I'm good to go. If you didn't get the same p-value, you should probably check, one, did I type everything in correctly? And two, what did I do incorrectly? Maybe you forgot to use the pooled proportion. All right. Maybe you used the pooled proportion too much. And you used it in your numerator, not just in your standard error or your standard deviation. So I would state always do it by hand first, and then after you get the calculation, you can go ahead and use the calculator program to check your work so that you don't forget to state everything that you need to originally. Okay. And that's the same thing that this AP exam tip is saying. So, as a small refresher, this is the formula to find our z-score for a two-sample proportion. Finding that pooled proportion will help us first, and then we're going to use it to find our standard deviation. And then we'll take our z-score, whichever our alternate hypothesis is. Maybe if it does not equal greater than or less than, we'll decide which way we shade with it and get our p-value, which ultimately helps us determine, do we reject the H naught or do we fail to reject the H naught? So here is another example. High levels of cholesterol in the blood are associated with a higher risk of heart attacks. We will use a drug to lower blood cholesterol, reduce heart attacks, and we're asking, does this drug reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. The volunteer subjects were assigned at random to one of the two treatments. 2,051 men took the drug to reduce their cholesterol levels, and then there's a control group of 2,330 men who took a placebo. During the next 5 years, 56 men in the group that got the drug and 84 men in the placebo group had heart attacks. Yes. Do the results of the study give convincing evidence at the alpha of 0.1 significance level is effective? And then the second one is interpret the p-value that you got in part A in context of experiment. So, part A, we're going to go through state, plan, do, conclude. All right. So, state, first of all, your hypothesis that, okay, they're going to be equal. You could either write as PG minus PL is equal to 0, or PG is equal to PL. Either one. The alternative one is that, well, we think we're going to reduce. We're hoping that this does reduce. So we're hoping that PG is less than PPL. So we start there. So we're really looking for a negative number, hopefully, here. Then we state, well, what PG is, the true heart attack rate for middle-aged men like these who take gemfibril. I'm obviously a math teacher, not a doctor, so I'm not familiar with all those biological terms. PPL is the true heart attack rate for middle-aged men like these who take a placebo. And again, we have to state our alpha level before we do any calculations. So our alpha level is 0.01 here. We're going to do our plan. So we have a 2-sample z-test. So I state the name of the test and then check my conditions. Volunteer subjects were randomly assigned to the two groups. And I'm checking my large counts. I'm going to do my p hat c, so that pooled proportion, to get what that is, and that's what I end up using actually. So I do my large counts n times ng times that. Again, I show my work. So I state the variables I'm using, then show the work, then multiply them together to get 70.35. I'm going to do that for all 4, and I see that they're all larger than 10. And so since they're all larger than 10, our conditions are going to be met there. Also remember that if you're sampling without replacement, I just put this in just as a reminder. Don't forget about your 10% condition. That the total number of people sampled here or in this experiment is going to be less than the middle-aged men. Now, think about the difference in this problem as before. We're not actually taking a sample. So if I'm not sampling without replacement, I technically don't need this 10% condition. But I think some of us get confused when to use it, when not to. So you won't lose credit for it, because I mean it is a true fact regardless that the total number of people is less than 10% of middle-aged men, but it's not required when you're doing a experiment versus when you're actually sampling without replacement. Because the whole point of this 10% condition is to make sure that our samples are independent and the probabilities don't change when we sample without replacement. So As we get the state and plan, we can now do the calculations. So I have PG, P hat or P hat G, P hat for the placebo, and then my pooled proportion here. I then will plug into my formula. Z is equal to all this. Again, in the numerator, I get a negative number. So it shows that the probability of the proportion of people who took the drug and had a heart attack is less than that of the placebo group. So since this is a negative number, again, I do have some evidence right now. Now I'm doing this test to see how strong is that evidence. Okay. I use my p hat c, the pooled proportion, for my standard deviation and get that equation. So I get a z-score of negative 2.47. Now, since my alternative hypothesis was that it is less than P1 is less than P2, essentially, I'm going to do the same thing here. I'm going to take the probability that Z is less than this value. So if I use a table, I get it comes out to 0.0068. I could use technology to be, my lower bound is negative 1,000. These two should be negatives. I'm sorry for that. It should be negative 1,000. Upper is negative 2.47. My mean is 0. My standard deviation 1. I get the same exact value out. And then I conclude. So this value here is my p-val, right? It's a probability that Z is less than that number. That is my p-val. So because our p-val is 0.0068 is less than alpha, which is 0.01, we reject H naught. There is convincing evidence of a lower heart attack rate for middle-aged men like these who take gemcitabine than those who take only a placebo. Right, so just to make sure we're clear, when our p-hat is smaller than our alpha, we reject H naught, and we have evidence in favor of the alternative hypothesis. Okay. So then part B is, what does this p-val actually mean that you got? So remember, the whole point of all these statistics or tests that we're doing is that we're assuming the null hypothesis is true. So I'm assuming there is no difference, that they are the same. And then I do my test and I see, okay, well, assuming that they are the same, the probability of getting something this small by chance alone is 0.0068. And that's pretty small. So since it's pretty small, that's how we have significant or significant evidence that, hey, these probably aren't the same, because the probability of it just happening, given that it was true, is so small. Well, then there must be some other reasoning, and that would be that, hey, maybe PG is really less than the placebo. Okay, and that's all we have for today. So hopefully you should be able to state the appropriate hypothesis for a difference between two proportions, determine whether the conditions are met for performing a test about differences, calculate the standardized test statistic, that's our z-score, then use the normal curve to find our p-value, the probability of getting a z-score that small or that extreme, depending on your alternative hypothesis, and perform a significance test about the difference between two proportions.